So in Monday, we talked about this posterior. So we find the Pareto optimal solutions before we make the decisions where to go to select the final solution. So here, the final solution is selected after we run the optimization. But then we also talk about that in a period, quite common in other single objective function, you put the weight, but this weight need to be decided before you run the optimization. So I was not able to run this video, but now I hope that, let me see. I explain a little bit more about, we explain quite much about the right-hand side. So you understand the logic, how we, based on different weight combinations, that the optimization, single objective, will find the solution that was more favor, more bias towards the reagent that you have your weight combinations. So the higher the weight for certain objective, the higher chance that you find solution more favor for one solution, but not the other. Now, this animation is coming from full optimization. And as you can see now, the main change of the weight are only on the throughput. And then you gather from full optimization and then run an animation. And now I start the animation. I hope that you will see that. Otherwise, you need to let me know. When we run the optimization, each of them will, based on the weights, try to find different location in the search space. But you can see here, when the optimization start to become mature, what we call converge, then you will see that the more or less now the color, the circles will not change that much, because when the optimization start to locate the solutions based on the objective, based on the weight combination, you will see that the optimization to the end will mainly focus in certain reagent. And that's why with single objective, you are not possible to find the whole Pareto front, because the weight will bound the optimization so that when you converge, you will just focus on certain reagent in a search space here. And in all these cases, we just show two objectives. Sometimes we just call it bi-objective, but you can imagine the same behavior will be the same whenever you have a many objective. That means you can only focus on certain reagents of the Pareto front. So this was the animation I promised to show you back in Monday. And then later, I think today I have some other animation to show you, especially something related to more industrial applications. And I think we talked about this, about the mathematical relationship here. Now for today, we can take a closer look on the common algorithm you're going to use. In this course, it's not very deep, so you don't need to go down and look at some MATLAB or C code, how the implementation is made. But NSGA2 is the most common, well-seated, I think just this paper, NSGA2, you find this paper, 2012, by Professor Depp, we mentioned several times. Fast elitist non-dominating sorting genetic algorithm. And then the first version, now with 2, that means this is the second versions. But with this is the second versions. And then what the second versions have included is fast elitism. And what is meant by elitism in multi-objective optimization? We talk about non-dominating sorting. That is one very key component of multi-objective optimization. So not all algorithm, but most of the algorithm in the same generation as NSGA2, they are based on this mathematical calculation called non-dominating sorting, which we explained a bit the math last time. But this time, I think in an algorithm, this is something that you must have, the fast non-dominating sorting. But the interesting thing is look at the algorithm, the pseudocode here. If you remember, when we talk about genetic algorithm, we talk about this selection, crossover, and mutations. So those will still be there, that whenever you talk about generate the offspring, so everything we talk about in an ordinary genetic algorithm, they are still here, but now we embed it into something called generate offspring. You have your parent generations, and then you use your parent generation through selection and crossover. Ordinary genetic algorithm principle, mechanism. That is why we have genetic algorithm here, right? So you generate a new generation, you call it QT. And you have the iterations values from simulation or other modeling, you get the iteration of QT. But now the interesting thing is in a multi-objective scenario, we have an additional step is we combine the parents and also the offspring generation or generated offspring. We do a fast logarithmic sorting. We sort them together based on the mathematical principle of dominancy. So this is not unique to NSCA2 or NSCA, but this is a one key mechanism that distinguish multi-objective genetic algorithm with other genetic algorithm. That is the first step. But this step will decide that the certain populations will go to from level 1, level 2, and so on. So when we talk about this level 1 and level 2, so the result will be look like that. So we have the P. Now I'm looking at this the right part here. From the P through the selection crossover mutation, we generate a Q, and then combined it with a P and Q, we do a fast logarithmic sorting. And then this logarithmic sorting will first identify if the first level logarithmic solution represented by the rosy area here, we put it F1, and then you have F2 and so on. Now, the interesting thing to note is you have P and Q. So together, the population size will be higher than the original population. So let's say that you have 100 in the populations, and now you do this sorting for 200 solutions. You want to cut where you want to cut here. Okay, so you need to decide where to reject. And then how you can base on this rejection, there is an additional mechanism called a crowding distance. Remember, without crowding distance, without this calculation, I don't think we call NSCA2 as NSCA2. Because of a crowding distance, it was a new invention compared to the first versions of NSCA that was just like have a genetic algorithm combined with logarithmic sorting. So what does this crowding distance mean? We go to the next slide. And then I think I told you something lie. I told you the paper was 2012. The paper was actually 2002. So it's already 20 years. So what the non-dominant sorting together with the crowding distance, what do they do? Now, with non-dominant sorting, we are talking about convergency. Convergency means that, look at this figure. So you could have solutions that give you good convergency. That means you will be pretty much lie on the, now I'm showing this reagent, if you see here. So you get some sort of clusters. Yes, I think they align on your target Pareto front. If your optimization is not good in convergency, then you will find it most like here. So if you have an ideal front, normally real practical application, you don't know where this front lie on. Nobody knows, as my previous professor, he liked to say, nobody really know where are the real Pareto front. But let's say that you know about the front, you have the certain target. Convergency will lead it to be closer or even lying on your Pareto front. This is what this figure are showing. But with a good convergency, only with non-dominant sorting, but without another mechanism, and in here we talk about crowding distance, then the effect will look like this. That means your solution will be not widespread, or in technical terms, we call diversity. So we need to have both good convergency and good diversity. So like on your left-hand side here, so this will be a good algorithm that gives you the balance of both good convergency and good diversity. And lacking one of them will lead to something in the middle, and lacking both of them, a bad algorithm will be like that. And that is also something you can judge by when you run the optimization. Sometimes you're pretty lucky if you find that when you run the optimization, you end up finding a very smooth front, something you can do it in the lab, so you find that is a very smooth. But in real life applications, usually it's difficult to get a front that will be very smooth, or you need to run pretty much time. So crowding distance will help you to do this ranking, non-dominant sorting, and then the counting distance. I think I jump over this slide because I think this slide simply repeats something about different rank in a more colorful way. Some of you, if you have done a course with Sunif Bandaru, I think this slide was something he showed in his course called Computational Intelligence. But I know that only a few of you, one or two, attended his lecture. So the non-dominant sorting is like putting the mathematical formulation into a pseudo into the code. So in some other courses, I ask the student to use whatever language they like. I give them a data set so that they can do the sorting themselves. But in this course, I will let you see that when you run an optimization using facts, then this kind of coding will be already embedded in the function. I will later show you how you can activate these functions. But either by checking this code on the slide, or you can check the original paper by Professor Depp, you will understand better how he has an efficient way to do the non-dominant sorting. And that's why the way that he did the sorting based on the smart way to first sort the solution in one objective and then sort it to another, the sorting can be a bit faster. That is called a fast non-dominant sorting. Otherwise, using some stupid way, if you have many solutions to sort and then you run it over multiple generations, then you will not be efficient. And then we talk about the counting distance. So these two solutions, of course, we will choose the extreme solutions. That is what we mean by 1 and P. So this counting distance, because of those solutions, has nothing to compare. So the counting distance is called infinite. But if you look at this solution here, so this solution together with these solutions, so their distance will be larger than if this solution together with these solutions. So if you make the calculation of the distance among the solutions, and then you also sort them according to their counting distance, then some of the solution in the middle, like the P here, will be taken away. The reason was because of we want to select the solution that can give us the highest diversity, spreading good across the Pareto front. And that's why the counting distance is a mechanism that promotes the diversity. And then together with the convergency, it will make the front look more smooth in order to save the solutions, the number of solutions that appear in the populations. Now, quite much about the NSCA2, and then I'll show you about the comparison of single objective, multi-objective. Now, this is something new. I don't think I summarized in this good way in previous lecture in Uppsala University. But starting from this January, when I start to make a talk for a UK network, I start to summarize why we use a multi-objective optimization for production and logistics system. And then the emphasis here will be why, okay? So Matthias start to talk about some factory physics, which is my favorite subject. I will go much deeper to talk about more principles in my own course when we talk about factory physics. But later I will show you a slide relating to the whole supply chain so that you can see how we relate what we mean by multi-criteria is something inherently in many problems you find in production and logistics. Especially you will consider that in most real-life cases, you don't just optimize and study one goal. You have a multiple goal. Either you want to compare, you want to find a trade-off, or in another case I talked about in the second point here, this is more about, it's not only about finding the optimal solutions and then make your decision. It's also about eliminate the corrupting influence of variability and then useful for self-benchmarking. So when I talk about here, self-benchmarking, I don't know whether you understand what I mean. I will use some picture to explain more details. And then based on this, we can also use a multi-objective optimization to have a more fair comparison of different strategy. And this one, I also have a more slide to show you before the break, so we will complete these discussions. I think the first part we already talked about, and then now in the coming 30 minutes, I will give you more discussions about the second point and the third. And then after we come back from the break, then this will be the key topic that we should cover today. How we can use multi-objective optimization for bottleneck analysis. When I talk about bottleneck, if you have studied industrial engineering before, maybe you have heard about the terms, and then maybe in common sense, you use the word, so bottleneck. But exactly what we mean by bottleneck in a logistics, production, supply chain system, and then why it is so interesting to relay, that is why I call LOVO, multi-objective optimization and bottleneck. So we will talk about it after the break. Now, uh, I think later I will remove this slide, but even though I mentioned a bit about my research roughly, so this is not a real research course, but I want to tell you that this topic, multi-objective optimization, in the last 15 years, produced me 13 PhD theses. And then most of them, they are still in academic. Many of them were in industry as well. I mentioned about Leif Persson. So this picture in the middle was by Leif. I mentioned that he's now a CEO of a company. IDC is an industrial district network in this Scholar Borley, in this Southwest region. So he's the CEO of that company. So this picture was defined by him in his thesis. And then in this course, pretty much we have covered about simulation-based optimization. We didn't talk a lot about sustainability, how it model. Maybe Matthias have talked about that combined with cost. But in his thesis, he relay how this lower level bottom modeling can go up to the optimization. And then it will be in my next course, then I will more focus on this post-optimality analysis. But anyway, this is a topic that is quite serious. It produced me with 13 PhD theses in the last year. So if you have the chance to do any PhD in Uppsala University in the future within this topic, multi-objective optimization, so I think most likely we'll touch a point, something I have done before with other students, and then make some extensions. Now, we look at several scenarios. I think I have covered some of them. And then we talk about this lean buffer and bottleneck analysis. So I think this picture was already talked about. And then when we compare lean buffer, which I will give you a demonstrations, in fact, which is an exercise you need to do in with 8.2. So this is something that you can taste yourself. We call lean buffer. The term lean buffer appeared in Leif Persson's thesis, but it was not his term. I think the original term came from a textbook called the Production System Engineering. I have a picture of that textbook later. But that textbook, what's meant by lean buffer? It means that the lowest number of buffer allows you to achieve the target. We will do the demo together, and then we will go to bottleneck analysis. Now, I think I jumped to this picture so that I continue some slide that you haven't seen. For a supply chain system, you may look at it as a network of these objects. So somehow, even though we just have a few objects here, we have the process. In some other modeling, they call activity. And then we have the buffer. Sometimes you may call it inventory. But stock point is better to be talking about the end. You can see that it's in the end of your net, what do you say, a factory or a unit in your supply chain. One of the unit in your supply chain, you have the end stock point. They will have a little bit different from the buffer because the buffer serves the purpose as the cushions to absorb the disturbances from your process. But the stock point may be different. The stock point there, the purpose is to waste either from the transportations or, like in this case, is finally deliver to the customer. And no matter you talk about push and pull system, so if we have the market demand and then if we pull from the stock, so this is the classical make to stock situations. But you also have a make to order is also the same, but then you will more emphasize on the right to left. Sorry, in this case, it's a left to right. So the direction of the make to order is like that. And then if you go for a pull make to stock, then I think the signal propagate from downstream to upstream. But no matter what you define here, we can safely formulate them into some common objective. Here, I think this is a repeat of the factory physics slide. Matthias should have talked about this is a correlation between work in process cycle time and throughput. And then this is the optimal trade-off. I think I'll just go to the slide that you haven't seen before. I think this one is something new. I'll start to use this slide as mentioned in February when I start to have a talk for UK network. So this was the cycle time against throughput. Now the supply chain problem, why we can naturally formulate into multi-objective is because of, you see, cycle time and throughput, they are in conflict with each other. And then when you look at the right-hand side, so just by cycle time and utilizations, so you can plot it in this way. I think I just stimulate a little bit how you should look at this diagram. We require a little bit training because of the cycle time is to minimize and then the throughput is to maximize. But in this case, you have to reverse. So you minimize your cycle time and you want to maximize your utilization. So I think you can actually put it in the swap the X and Y axis, and then the curve will look like the one on the left-hand side. And then of course, the utilization is something that can be correlated to the throughput. So that's why things here are correlated. But even though they are correlated, but which objective you look at, and then which objective to help you to make the decision, that would be something you need to think about. And then is a very important message I tell you is both in this course and then in my other courses in the next course, I'm teaching you not just about a method called multi-objective optimization. And then of course, it's not a silver bullet. So if your problem, as we talked about last week, if your problem is not quantitative, if you cannot formulate an optimization problem, so the method I'm teaching you is not useful. But what I'm teaching is not only about a method, it's also a way of thinking how you attack a problem. The way of thinking is how you can find in the problem, are there any one objective or are there many objectives? And then what are the objectives and what are the things that you can make decisions? So in these figures here, you don't see anything you make decisions that you call decision variables. But you see that by combining the different objectives, some of them may be important for your problem, some of them may be not important, but they are the general problems or the objective you can find in a supply chain. For other system, of course, you may have other objective. Let's say that for a hospital, I think you probably will relay this cycle time less. I think how long time the patient stay in the hospital. Maybe cycle time is not something like a primary your concern in your hospital for some patients, because for some patients, their major concern will be the waiting time. How long they wait in the queue, how long they wait until they can get into the operation theater if they need operation. So you don't see the waiting time here. They can correlate it with the cycle time. But what I mean is for other systems, you may have other objectives, but in general, for supply chain, these are very general. Now, the stock point and surface level, I don't know if Matthias has covered that in his slide, but today I give you some recap here. Is the surface level is equal to your demand minus the number. Now, sorry about the picture. This should be minus about the toddy job. Let's just put a T here. D minus your toddy job, and then divided by your demand. Okay. Now, remember when we talk about surface level, the target, the ultimate goal is 100%. For collaboration with IKEA, when we work with their factory, usually they don't really bother or not look at throughput, but they are very careful about the surface level. And of course, I will not tell you about the surface level of their factory because when we did some consultancy for them. But we imagine now we're talking about 30 job. I don't bother whether my job is delayed 1 minute or 2 minutes or 1 hour or 1 day. As long as it's delayed, then it's a 130 job. And you have another measure called the tardiness. to calculate how much your job has been delayed. But in here, we only bother about the number of product we order, the demand, and then if any of those jobs that delay after the deliver, after the due date divided by the demand, that we call them 30 job. And if you have a 30 job equal to 0, then of course, then you achieve 100% surface level. The basic factory physics principle is stock inventory and surface level. They are conflict in this way, so that if you want to have a very low stock level, you want to minimize here, then you end up with also risk have to have a lower surface level. And then if you aim at increasing the surface level, one thing very simple for many people in the industry they would do is to increase the stock inventory. But of course, this violates certain lean principle, which may not be desirable. So this is a general relationship between surface level and stock level. But then on the right-hand side here, you will also see that stock inventory can be related to this backlog. Now, backlog also means the delayed job. So in this case, I think we just backlog is exactly the same term as what we talked about 30 job here. So this is another way to put it. So in this case, we are not calculating the surface level. We just use the 30 job to talk about here. Now, when I show this slide, now I think it's already too many things I point out here. I mentioned that this will be useful or insight, give you some insight. That's what I call give you some insightful view. Why is it insight? Because when you increase any variability of your system, you actually will have your optimization showing your result will have the system degrade. Why this is degrade? Because now with the same throughput, if you cut a line here, as we discussed the last time, how you look at that, now it costs you much higher cycle time in order to achieve the same throughput. And then here for the surface level, it's the same here. Now, if your system degrade because you increase variability, then you see that it costs you more inventory in order to achieve the same level. So it used to be like that, but if your system degrade because of increasing variability, then you end up have need to spend more inventory, maybe even it can be interpreted as a high inventory cost in order to get the same surface level. So this figure will be very useful from a theoretical factory physics principle. So we illustrate how the corrupting influence of variability, one chapter name, I don't remember, it must be chapter 3 in the factory physics textbook. So the corrupting influence of variability. But I don't think this figure, this kind of insight will be useful in practical case. And that's why I changed this diagram in this way, which is also a way I try to teach you how to think about solving a problem. So imagine now your system in the black line. So you have your system variation, you have your system parameters that you already have a certain setting. Okay, good. When you run some optimization, you get your black curve. So this is where your system like today. Okay, so instead of looking at it from a corrupting influence of variability, I think the $1 million questions that many industrial engineers ask, and sometimes it's really $1 million. The reason was because, let's say that if the company want to invest, buying new machines, hiring new workers, adding a new shift, and then you even maybe talking about connecting to a new supplier, maybe talking about even pull your sources, your components from multiple suppliers in the supply chain situations, then you end up with asking yourself the question is not what happened your system degrade. Your question to ask is how you improve your system. And that's why the more important, more proactive view by using multi-object optimization is today you have your system like behaving in the black curve. What would you do in order to make your blue curve moving towards the, your black curve moving towards the blue curve? So this will be very interesting here because whenever we find where to reduce the variability and then optimally reduce the variability. Then we shift the black to the blue. So I made multiple illustration here to let you see the benefit. So how you can from a certain point here, let's look at the infantry point. Now it's not degrading, but improving so that you can achieve the same surface level, but you keep dropping your stock infantry. So this is not something you will learn from lean manufacturing. Why? Because lean manufacturing, they does not really rely on the dynamic simulations or modeling, and then they also could not rely on this optimization in order to observe the behavior of the system. Lean manufacturing emphasize on try and error, and you need to make the change. You don't afraid to make the change in the system, and then you will learn something. But in here, I think my message to you is we want to learn something. Yes, this is the same lean principle, but we want to learn it from modeling and optimization, not from doing try and error or experiment with your real system. Now, I also give you another interesting aspect. I talk about that why multi-objective optimization will also eliminate some principle that you will not find in other optimization. I have a real system, or let's say that I think is a model that we got a company from a company in a research project. The optimization was not very difficult. We had the number of conveyors, and then the conveyor speed will can be adjusted by adjusting the speed of the motor, so that if you want to have a higher speed for the conveyor, then you can also decide to go for higher speed. And then the decision making for the company will be the combinations of the conveyor speed together with a few buffer. And now there are not many buffer. And then you see the blue side is more like an infantry. Okay, so it's not a very big size problem. But what is interesting, and then I try to eliminate by giving you this highlight here, is without multi-objective optimization, since we have this as the objective, and then because of the diversity that the optimization want to achieve, that will give you this very nice curve. So without using multi-objective, you will not get the so dense lines to show you the relationship. And then without this dense line, then you will not observe something very interesting. Is we see that there is a conveyor called number 6 on conveyor number 7. So I think this conveyors, I don't see number 6 here. I think number 6 is somewhere here. And then number 7 is somewhere here. Now I try to highlight here. But the most interesting aspect to observe is in the beginning, I think the improvement of the throughput was gradually, even though it's improving, but it's actually not very fast. But suddenly there is a big jump after the conveyor speed come to a certain level. And then after the conveyor speed past this 100 millimeter per second, so 1 meter per second, after passing this point here, you could find that increasing the speed of the conveyor is meaningless. The effect of the buffer is not so clear. The number of pallets, of course, this is directly proportional. I think this effect is anticipated. But where to find this kind of sudden change of the improvement? And then here, again, you have a similar relationship with a conveyor 6, but the speed need to be a bit higher. And then later, where is the saturated point? So these are the practical things you can get by using multi-objective optimization. And then if you just use single objective, because you will not get this curve, so you will not also see this one. And then I have some discussions about this comparing strategy. If you compare B and A here, so you may say that, okay, B and A, they are non-dominant each other because of B here will be good in the throughput. B is good in the throughput, but then it's not very good compared to A in terms of the buffer. So A have a lower buffer, okay? So one of them gives you a lower buffer, and then another one gives you a higher throughput. But can you now conclude that the strategy, different strategy represented by B and A will be like this? Can you make a general conclusions about the optimal setting about these two strategy? No, you cannot just compare with one solutions. And that's why in this figure, we highlight that you need to compare the optimal Pareto front in order to observe this A is in general superior than B. Okay, even though some of them like A3 is lower in the throughput, but in general is superior than B, the strategy called a B. But the funny thing will be like this one. There's nothing to forbid you to have a system behavior that like this is certain strategy, they favor you for one objective, but maybe inferior in another objective. Let me give you a practical production or supply chain problem. If we have a system that uses a Kanban, let's just easily combine Kanban and then the factory physics concept, constant work in process, and also push. We talk about push, and then Kanban is a typical pull mechanism. So in general, you can see that when I circle this reagent, the green part here means that the Kanban in general is more superior in lower the cycle time. But then there is a crossover point somewhere here that even though push system in general is not recommended by industrial engineering professors, they always say that pull is better than push, and then lean is better than make it to order and so on. But anyway, the interesting thing here to observe is if your target is to have a very high throughput, then Kanban is actually not a very good strategy. So ultimately, every system will be saturated when you have enough cycle time, when you have enoughly long cycle time. But you can see that Kanban favor cycle time, but then is inferior in the throughput. And on the right-hand side is some figure from my research result on a paper that I published in 2012. But here simply means that I made some statistical calculations in order to make sure that the result is valid. So the crossover point that I show on the left-hand side, something we call attainment surface, is actually very clear, shown in this calculation. And then this calculation is made by some statistical difference test. So that's why it's also statistically correct here. Now the time is 13:55. Let me see. I think when we come back here, I think I will go directly to do a demo. So, but before I give you the break, do you have any questions to ask me? You can speak out or put it on the chat. The demonstration is about a line which you are going to build yourself in 8.2. I don't remember exactly, but I think it must be this setting that you will try first. So you have the availability 90% and the MTTL 5 minutes. Make sure that is 5 minutes, not 5 seconds. Okay. And then this is a quite balanced line so that you will know that in the lab instructions 8.2, we talk about the processing time of each operation will be the same. I hope I remember right, but the processing time for everyone is the same. And then it should be 1 minute. So that means 60 seconds. So if I'm not wrong, I think that means the target throughput, the optimal throughput without the availability issue will be 60. So you can expect that for an ideal line with a 1 minute with the processing time here, we will expect the throughput will be 60. But industrial people, they will know that with the availability 90%, they will just say that, oh, your throughput will be 60 and then times 0.9 because you have in general, your availability is 0.9. I want to tell you that if you believe that this calculation will give you your throughput and then you have no need to do any modeling simulations, I can tell you that this will be wrong. This will be wrong because of you have a connecting effect of a different availability. So when you have a longer line, when the availability issue, they propagate to each other, then it will make it less, even worse than 0.9 if you just calculate one of them. And then what throughput you will get will be very determined by your buffer size. So this will be what my demonstration is about. So let me know if you have any questions. If you don't ask me anything, I think we can still make use of this few minutes before the break to show you the model. I will not guarantee that this is 100% same as what you are going to do in the lab, because sometimes I change the setting. But if you, I hope that you see is big enough. Is 1 minute here, so I didn't tell you a lie. So I think everyone is 1 minute. And then if we look at the availability setting, so be careful that when you first do the simple experiment with a 8.2, chapter 8.2, if I remember correct, this will be 100. So you are going to see that if you have 100 availability, then and then now every stations have the same processing time, then it really doesn't matter how you have the buffer, because as I mentioned in the instruction note, you will get the zero buffer occupations because of let's imagine you don't have any availability issues, and every of them, every one of the station, they have the same processing time. Then what will you get is something we call a well synchronized line, and closer to, in industry they call transfer line, and in this case you don't really need the buffer. So you need the buffer, when you find that you have this availability issue, and that's why I go back to change this to 90, and then the MTTL, it must be 5.00. So let's see. I hope that you know that you can use the control button to click on all the operation, and then to make sure that all of them is the same. But now, since I now see the number 90% in availability and then 5 in the MTTL 5 minute, so in this case I'm sure that they were the setting that I'm supposed to use in 8.2. So when we come back from the break, I will immediately show you a quick demonstration. But even without the demonstration, I think many students, they managed to complete the 8.2 without any problem, because it's very easy. But I will show you how we set the multi-objective scenario. We choose the NSGA2, and then we will use some default setting, and then we will run the optimization. We will let the optimization start. So now, if you have any questions want to ask me, put it on chat. And then I think I get the questions now, but I will come back. When I come back, I will answer these questions. Now we take a 15 minutes break. I will. I think the questions are about get back on the slide with buffer 6 and 7 optimization graph. I don't understand these questions about buffer 6 and 7. Maybe I would buffer 6 and 7. I don't understand these questions.
Sorry, could you back to the previous slides? I mean that in the and one more slide previous. In here,
Yeah.
in this question, we have to. I mean, convoy or not buffer, but I think I didn't get this. This slide so good, and I don't know what's the meaning of blue and orange points, and what does this graph really shows. I didn't get that. Is it possible to come again earlier?
I think yeah. Sorry if you are not familiar with looking at this now. One thing maybe I missed to explain very clearly is the x-axis and y-axis. Now, this x-axis here, they are the decision variable. This is a common way that when you put something you call a scatter plot. So these are the decision you made. So the x-axis, they are not the objective. They are the buffer size. Maybe I don't remember, but I don't think we need to bother. They all are something that you need to make decision. You need to design. So compare with the objective figures that we showed it before. Now this is very different, but the difference is the x-axis, they are the decision variable. And we want to see the relationship, how you change the speed. Let's still stick to this conveyor system. When you increase the conveyor speed, then you will increase the throughput. And this is the relationship you see here, okay? But we look at only the points on this front here. because we don't want to be trapped in this reagent here. We just look at the front. So increasing the speed, you will increase the throughput. But what is the relationship between the speed and the throughput? I think this curve will tell you. And then similarly, yes, you increase the pallet, you will increase the throughput. But then how much you increase the pallet, and then you want to achieve to the top here, you have a like a top level, and then it costs much more pallet in order to achieve a little bit higher. So this is the curve that tell you. So maybe your confusion is because of I didn't explain very clearly that the x-axis here, they are the decision variables. They are not the objective.
No, I got right now. I got that.
Yeah, and then the blue and the red, they are mainly coming from the optimization platform that we work with new solutions. Okay, now I think the color means something, but they are actually the same. Let's say that the throughput here, you see here, I think the color here simply mean the throughput, but you can change the color here in order to make a comparison on the third objective or on the third variables. Yes, thank you for asking me this.
Yes, so when we, for example, when we increase the speed of conveyor 6, the throughput will be increased, and the optimized points should be the line, the orange point on the top of the graph, something like that. It shows us. Thank you. Yeah, I got that.
Yeah.
Thank you.
So and then in real life, maybe you don't bother about all the solution in between, but in real life, you're really about the curve because it gives you the optimal relationship. Again, this is a relationship, but this is optimal relationship between your variable and also your target objective. Okay. Yeah.
Thank
so
you. Yeah.
we come back again. I think maybe Ada already have gone. I don't know. So, but we come back at 14:15.